Functions are often used to scale very large or very small numbers into numbers that are easier to understand, easier to wrap our brains around. So we're going to look at, actually, we're just going to look at two common models. For log functions, the Richter scale, which determines the magnitude of earthquakes, and finding the pH of a solution. Okay. We are not going to do the decibel scale. But that is another thing that we measure using a log scale, is the intensity of sound. All right, so can you give an example of a number that might be used to report the magnitude of an earthquake? 6.0. Yep. So seismologists generally determine the Richter scale magnitude of an earthquake by examining a seismograph. So this is an example of what a seismograph looks like. And the Richter scale defines the magnitude of an earthquake as the log of I over S, where I is the intensity of the earthquake and S is the intensity of a standard earthquake, the smallest earth movement detectable by a seismograph. So we compare how intense the earthquake was to the smallest earthquake we can record, and we compare those two, and then we take the log of it. Okay. So there are two. The intensity has a unit, like I don't know, meters per second or something, of how the Earth is moving. So the intensity's got some kind of a unit on it, and then the magnitude is unitless because we take the ratio, and the units are going to cancel. That's why they don't say a magnitude of 6.0, feet. There's no units on magnitude of an earthquake. So let's see. The 1906 earthquake in San Francisco had a magnitude of 8.3. And at the same time in Japan, an earthquake with magnitude 4.9 caused some minor damage. How many times more intense was the San Francisco earthquake than the Japan earthquake? All right, so they're not asking us to compare magnitudes, but they're asking us to compare intensities. So that is the I in the magnitude formula. So I'm going to analyze each of these earthquakes. So San Francisco and Japan. Okay, so my formula for magnitude is the log of I over S. Okay, so I'm analyzing San Francisco. They're telling me the magnitude was 8.3. So that is the log of I over S. What I would like to know is I, the intensity, okay, because that's what they asked me about. They asked me about the intensity of the two earthquakes. So when I don't put a base on the log, what base do you assume that it is? 10, okay, so there's a little 10 there. So now I want to know something about the intensity, so I'm going to change this equation to an exponential equation. What is the exponential equation that's equivalent to this one? Yeah. Yep. The base is 10. 8.3 is the exponent, equals I over S. And then if I want to know what I is, I just multiply both sides by S. S times 10 to the 8.3. And S is just some constant. I haven't told you what it is, but it's just some number. It's just the number that we use to measure the smallest earthquake. Both sides by S, this denominator, yep, to get I by itself. Okay, so I want you guys in your groups, analyze the Japan earthquake the same way. Find the intensity of the earthquake in Japan. So we write down the formula. Magnitude is the log of I over S. And then my magnitude here is a 4.9 equals the log of I over S. Change it to exponential form, and we get 10 to the 4.9 equals I over S, and then multiply both sides by S. So the intensity of this earthquake is S times S times 10 to the 4.9. All right, so I want to know, the question asked me, how many times more intense was the earthquake in San Francisco than the earthquake in Japan? So how do you find out how many times bigger one number is than another? Yep, you divide them. Yeah. Like if I said I have $5 in my pocket and somebody else has $50 in their pocket, they have 10 times more than I do because you divide 50 divided by 5 and you get 10. Okay, so I'm going to divide the bigger number by the smaller number to answer the question. So the S's cancel. So it turns out I don't need to know what that number is anyway. And then if I have 10 to the 8.3 over 10 to the 4.9, dividing like bases, what do you do with the exponents? Subtract. So this is going to be 10 to the, see, 8.3 minus 5 would be 3.3, but I'm not taking away 5, 3.4. 10 to the 3.4. So let's see what that is. 10 to the 3.4. Oops. 2,512 times as intense. So 4.9 to 8.3 on the Richter scale seems pretty small, but those are actually powers of 10 difference in intensity. So the difference in intensity is actually 2,512 times as intense. Okay, and we represent that with a relatively small change in the magnitude. So in general, increasing the magnitude by 1 when you're measuring earthquakes corresponds to increasing by the intensity by a factor of 10. Does that make sense? Okay. All right, so we also use logs to measure pH. Chemists use log scales to measure pH of a liquid, and pH is the measure of the liquid's acidity or alkalinity. So usually pH values are between 0 and 14. Pure water has a pH of 7. It's considered neutral. Less than 7 acidic and greater than 7 basic. So the way we calculate pH is you take the negative log of the concentration of hydrogen ions. So this notation just represents a number, and it's the concentration of hydrogen ions. And we measure it in moles per liter. If you've taken any chemistry, that makes sense to you, and if it doesn't, it's just a unit, right? So I want to find the pH of shampoo, and I know that its hydrogen ion concentration is 7.4 times 10 to the negative 10 moles per liter. I want to determine if it's acidic or basic. Okay. So pH is the negative log of the hydrogen ion concentration, which is 7.4 times 10 to the negative 10. So I have my calculator. I do negative log of 7.4 times 10 to the negative 10, and I get about 9.13. So is the shampoo acidic or basic? Basic. Greater than 7. So is that okay? Just type in negative log of the hydrogen ion concentration. And then what if I give you the pH and you want to know the hydrogen ion concentration? You guys try to do that one. All right, so if I write down the formula, pH is negative log concentration of hydrogen ions. And I know the pH, so I put in a 4.1 here. So when I'm trying to solve a log equation, the first thing you try to do is isolate the log. So I'm going to multiply both sides by -1. Then there's a little 10 hiding right there. When you're solving a log equation, the key step is to change it to an exponential equation. So what exponential equation is equivalent to this log equation? 10 to the negative 4.1 is the hydrogen ion concentration. Yeah, once you do a couple of these examples, yeah. Oh, yes. Yep, you could put the -1 on the hydrogen ion concentration, yeah. Yep. So let's see, 10 to the negative 4.1. Oops. We get 7.9 times 10 to the negative 5. Moles per liter. Does anybody have questions? Okay, well that finishes up. Oh, well, sorry. Increasing pH by 1, so like if you increase your pH from 7 to 8, that corresponds to decreasing your ion concentration by a factor of 10. So that finishes up our class 39. Moving on to class 40. So we're going to talk about 2 new kinds of functions, power functions and logistic functions. We're not going to study them as in-depth, nearly as in-depth as we've studied all the other kinds of functions we've talked about. Just to give you a real brief look at what the formula looks like and what the corresponding graph looks like. And then we're going to do some data fitting. So a power function is a function whose output is directly proportional to some power of the input. So it looks like this. F of x equals k times x to the p, where k and p are constants. Right, so the only difference between this and a monomial is that that p number doesn't have to be an integer. It could be a fraction. It could be a negative number. So some examples of power functions would be pi r squared. Okay, so k is pi and p is 2. Or f of x equals 2 is a power function because you could write it as 2 times x to the 0. K is 2 and p is 0. And 2 square root x is a power function because I could write that as 2 times x to the 1/2. And 1 over 3x is a power function because it could be rewritten as 1/3 times x to the negative 1. So any function that can be rewritten like this. K and p are just numbers. So the most important thing determining the behavior of a power function is the value of the exponent. That's why they're called power functions. Okay, so these are the graphs of power functions where the exponent is 1 and where the exponent is 0. So if the exponent is 1, you just get y equals x. And if the exponent is 0, you just get a horizontal line, y equals 1. And those are sort of like boundary lines for different values of p. So in these cases, all of my power functions are just increasing. So when p is bigger than 1, they just go up. And if p is less than 1, these are actually like square root. They look kind of like the square root function. So bigger than 1, they look kind of like polynomials, so increase without bounds as t goes to infinity. And when p is less than 1, you get things that look like the square root function. Again, looks like the square root function. And if p is negative, you get graphs that look like 1 over x. We haven't studied 1 over x in class, but you have seen it like in your transformations project and a couple of other places. So negative p's look like 1 over x. All right, so why have power functions? Well, sometimes a power function is the best model for data. So for example, we have planets and their distance from the sun as our x value, and y is the time required to orbit the sun. Okay, so there should be some relationship between how far away a planet is and how long it takes to orbit the sun. So if we plot the data, you get a scatter plot that looks like this. A line doesn't quite fit. A quadratic is a good fit, but it's not perfect. So if we do linreg and quadreg, roughly speaking, the linear function is too slow and the quadratic function is too fast. So we can do a power regression. In your calculator, one of the options is power reg. And it turns out that that is the best fit. It allows us to find a power function to model the planetary distances. Enter the data in your calculator, use the power reg command, and you get y equals x to the 3 halves as your formula, and it has a nearly perfect r squared value. Here it is superimposed on the scatter plot. Goes through every data point. So power functions just gives you another option when you're fitting curves to data. One more option would be the logistic function. So logistic functions are often used to model population growth. Initially, population may grow slow, but then the rate of growth gets faster and faster. But if a particular region becomes heavily populated, then the population eventually levels off, grows slower and slower as resources become more scarce. So here's an example where I have yeast plant growth over time. So I've just got several time plots here and the population size plotted on Y. And you see that like increase, it grows very quickly at first and then levels off. So the general equation for a logistic is C over 1 plus AE to the negative BT. You're not going to have to use this too much, but your calculator does have a logistic regression option. So if you see data that has this classic S-shaped curve, you might want to try fitting a logistic curve to it as opposed to a cubic. So if I do logistic regression on this example, the yeast growth example, the calculator would give me this formula. So in general, when you're fitting curves to data, First thing you got to do is enter the data in your calculator and look at the scatter plot. Okay. Once you look at the scatter plot, decide what sort of function to use. So you want to take a look at the general shape of your data and say, that kind of looks like a logistic or a quartic or an exponential. So I gave you a little chart here that gives you examples of data that you might use for various models. So you're going to look at your data and say, oh, my data kind of looks like this cubic one because it's got two peaks, right? Two extrema. Or my data just strictly increases, so it could be power or it could be exponential. And then you just try them both and use the one with the better R-squared value. So you go to the Calc menu, select the appropriate option for the type of function that you chose. The calculator will give you an equation for the curve of best fit. Then check the R-squared value and how well the graph fits the data. So some considerations that will tend to lead to a better model. The more data, the better. If there's a theory-based reason to use a certain kind of function, like quadratics for projectile motion, for throwing a ball up in the air, that's a better model to choose. A simple model that fits the data reasonably well is preferable to a complex model that fits it slightly better. Okay, so if you're choosing between an R-squared of 0.92 and 0.95, you might go with the lower R-squared if the model is significantly easier to work with. So that's a judgment call. And generally, using models to find values between known values is much more accurate than using them to make predictions outside of your data set. So sometimes it's not clear from the scatter plot what sort of function might be best. So you might narrow it down to say exponential or power. And then try them both and see whichever one has a better R-squared value. All right, so these are a little chart to help you choose what kind of regression you want to do. Your calculator in the stat calc menu has all of these possibilities for regression. And I want you to try fitting some data, fitting some curves to data. You've got 1, 2, I think you have like 5. Well, I don't know how many. You've got a bunch of data tables, fit some curves to each one.